Welcome back, my friend. In January 1995, the SS Lima entered a vast, glowing sea east of Somalia. Tonight, we follow the ship's report and the satellite image that finally confirmed the sailors were telling the truth. Settle into a comfortable position, soften your breathing, and let the quiet ocean carry you towards sleep. Subscribe to Deep Sleep Storytelling for more peaceful journeys through history, science, and the mysteries of the sea. "15 minutes to the White Sea." 10 years after scientists carried a bottle of glowing water away from the Arabian Sea, another ship entered the same mystery. This time, the vessel was the SS Lima. It was January 25th, 1995, at approximately 18 UTC. The merchant ship was traveling through the northwestern Indian Ocean, about 150 nautical miles east of the coast of Somalia. There was no land in sight, no harbor light, no distant city, only open water surrounding a modern steel hull. The sky above the Lima was clear. There were no low clouds to reflect the vessel's lights, and no approaching storm to disturb the horizon. The night was moonless, leaving the sea almost completely dark beyond the small illuminated areas around the ship. On the bridge, the instruments glowed softly. Numbers appeared on navigation displays. A compass showed the vessel's heading. The ship's position could be determined with a precision that earlier sailors could never have imagined. Radio equipment waited quietly. Charts rested beneath low lamps. Outside the bridge windows, the bow rose and settled with the long movement of the sea. The engines maintained their steady pulse beneath the decks. The Lima continued on course. Then someone noticed a pale brightness ahead. At first, it was distant. A whitish glow seemed to rest near the horizon, low and broad against the darkness. It did not resemble a ship's light. It was too wide. It did not flash like a lighthouse. It did not move independently across the sea. It appeared almost like a bank of fog illuminated from behind. Although the sky remained clear and the air around the vessel showed no sign of mist, the officers watched it. The lookouts searched for any ordinary explanation. Could there be land beyond the horizon? The charts showed none. Could distant fishing vessels be lighting the sky? No cluster of lamps was visible. Could moonlight be spreading across a layer of cloud? There was no moon. The glow remained ahead of the vessel, pale, uncertain, wide enough to become part of the horizon itself. The Lima did not alter course. Its engines continued turning. The hull advanced through dark water, while the white region slowly approached. Or perhaps the vessel approached it. At sea, especially at night, distance can be difficult to judge. A light may appear near when it is far away. The haze may seem fixed until the ship enters it. The crew could not immediately tell whether the glow lay close ahead or many miles beyond the bow. But as the minutes passed, it became clearer. The brightness was not in the sky. It was on the water. The ship was moving toward a pale surface. 15 minutes after the glow was first observed, the Lima reached it. There was no wall. No sharp edge rose from the sea. The transition may have begun gradually, with darkness beneath the bow weakening into gray. Then the water changed completely. The ship entered a milky white ocean. The glow surrounded the hull. It extended ahead of the bow and behind the stern. It spread to port and starboard until every visible direction had become pale. The crew could no longer see the ordinary black surface of the night sea. From horizon to horizon, The water appeared white. The lemur traveled forward across it, like a dark object passing over snow. That comparison entered the crew's description. The sea resembled a field of snow, yet nothing was frozen. The air remained warm. Waves still moved beneath the vessel. The hull rose and fell. Only the appearance of the ocean had changed. The water did not flash in the wake like ordinary bioluminescent plankton. There were no scattered sparks around the bow. The brightness was continuous. It appeared to come from the sea itself. The pale surface passed beneath the modern steel hull, just as it had once passed beneath wooden sailing ships. But aboard the lemur, the scene was framed by a different kind of world. Electronic instruments continued operating. The bridge clock marked the passing minutes. The radio remained silent, except for ordinary transmissions. Engine vibrations traveled upward through the deck. Officers checked the chart. The ship's heading was known. Its speed was recorded. Its position could be fixed. This was no anonymous vessel drifting through an uncertain region. The lemur was traveling along a documented route at a documented time. The old mystery had entered the age of precise navigation. Outside, the crew watched the white water. The vessel's dark shadow may have fallen across the glow. The bow cut through the luminous surface, but the brightness did not depend upon the disturbance. The water ahead was already shining before the ship touched it. The wake did not create the phenomenon. It only divided what was already there. The crew looked outward for some limit to the region. None was visible. There was no dark border ahead, no ordinary sea returning near the horizon. The whiteness continued in every direction. The ship appeared to be moving through an illuminated plain without approaching its end. Minutes became hours. Still, the phenomenon surrounded the lemur. The crew maintained normal operations. Readings were checked. Positions were written down. The course was followed. The quiet routines of merchant navigation continued within a landscape that seemed almost impossible. The contrast was part of the strangeness. Nothing aboard the ship had failed. The compass remained reliable. The engines continued steadily. The charts still represented the known geography of the ocean. Yet beyond the bridge windows, the sea no longer resembled the sea shown on any chart. A chart could record depth. It could show coastline. It could mark shipping routes and hazards. But it could not show a temporary white ocean formed by microscopic life. The officers may not have known how scientifically important their notes would become. At the time, recording the ship's position, heading, and speed was simply part of responsible navigation. Ships leave trails of numbers, latitude, longitude, time, direction, distance traveled. These details allow one watch officer to understand what occurred during another watch. They allow companies to reconstruct routes. They help explain delays, weather encounters, and unusual conditions. On this night, the same routine records preserved something far rarer. The White Sea did not exist permanently. It would fade. Currents would move it. The organisms producing the light would change. The region might be dark again before any research vessel could arrive. But the lemur's navigational record fixed the encounter to one place and one period of time. January 25, 1995. A clear, moonless night, approximately 150 nautical miles east of Somalia. A whitish glow, first seen ahead. 15 minutes later, a milky white sea extending from horizon to horizon. These details turned the observation into something that could later be tested. Earlier accounts of Milky Seas often contained uncertainty. A sailing ship might estimate its location from celestial observations. Speed, wind, and time. Clouds could interfere. Currents could push the vessel away from its assumed position. A log might describe a broad region rather than an exact track. The event could be remembered accurately, while its location remained difficult to reconstruct. The lemur offered something different. Its route could be traced backward. Its position could be compared with weather records. Its report could be placed over maps of the Arabian Sea. Most importantly, its location and time could later be compared with images collected far above Earth. The crew did not know this while they crossed the glowing region. They could not see the satellite passing overhead. They did not know whether any instrument in space was sensitive enough to record such weak light. From the deck, the event still belonged to the old world of sailors and witnesses. Human eyes saw it. Human voices described it. Human hands wrote it into a record. But those written coordinates created a bridge between the ship and a source of evidence that no earlier captain had possessed. The lemur remained within the Milky Sea for hours. The pale water continued sliding beneath the hull. Above it, the stars remained distant and dark. Inside the bridge, officers continued checking instruments while the vessel crossed a luminous region larger than they could see. Eventually, the ship sailed beyond it. The ordinary darkness of the ocean returned. The white surface disappeared behind the stern. Like earlier vessels, the lemur carried only its report away. But this time, the report contained a precise date, a position, a heading, a speed, a trail clear enough for scientists to follow years later. Sometimes the difference between folklore and evidence is not what was seen, but whether someone wrote down exactly where and when it happened. The faint mark hidden in an archive. Years after the SS Lemur crossed the milky white sea, its report reached a scientist searching for unusual light in the night. His name was Stephen Miller. He was an atmospheric scientist, interested in the faint signals recorded by satellites after sunset, small traces of light that could reveal fires, cities, fishing fleets, clouds illuminated by the moon, and other features hidden within darkness. Nighttime satellite images are not simple photographs. They are fields of weak signals. Some are real, some are distorted, some arise from the atmosphere, others come from the surface of Earth. To understand them, a scientist must learn to separate one source from another. A bright city may be obvious, a lightning storm may appear briefly, a fire may produce a sharp point of light, but the suspected glow of a Milky Sea was different. It would be faint, diffuse, spread across a large region without a clear center. It might be only slightly brighter than the darkness around it. For years, reports of luminous seas had remained difficult to confirm because they were temporary and remote. A ship could enter one, record the event, and continue onward. By the time scientists learned about it, the glow had disappeared. No research vessel could simply return to the same coordinates and expect the White Sea to be waiting. The phenomenon moved with the ocean. It formed, changed, and faded, but the lemur report offered an unusual possibility. The date was known, the approximate time was known, the ship's route was known, its position east of Somalia had been recorded. The duration of the encounter could be estimated from the vessel's log. These details made it possible to search backward through history. Instead of trying to find a new Milky Sea, scientists could ask whether an old one had already been seen from space. The search led to archived data from the United States Defense Meteorological Satellite Program. These satellites had been designed primarily to observe weather and atmospheric conditions. Their instruments could detect very faint visible light at night, including moonlit clouds and artificial lights on the surface below. They had not been built specifically to search for glowing bacteria. No engineer had designed them with Milky Seas in mind. The sensors passed repeatedly over the oceans, collecting images that were stored for later use. Within those records lay years of night skies, clouds, coastlines, storms, fishing vessels, fires, and other forms of light. Perhaps somewhere among them was the faint signature of the sea encountered by the lemur. The task was not simple. A weak, luminous patch in the ocean could easily be confused with something else. Clouds could reflect moonlight. Thin atmospheric layers could soften and spread nearby sources of brightness. Noise within the sensor could create false patterns. Large fleets of fishing boats could produce clusters of lights. Cities along a distant coast might brighten low clouds. Even the angle from which the satellite observed Earth could change the appearance of the image. The night of the lemur encounter had been moonless, which helped. Without moonlight, the open sea should have appeared extremely dark. That made an unusual region of brightness easier to notice. But darkness also made weak signals more vulnerable to noise. A pale mark might be real, or it might be an imperfection in the data. The archived images had to be examined carefully. One night alone would not be enough. A random sensor disturbance could appear once. A cloud could move through the region. A group of vessels might create temporary lights. What mattered was whether the feature behaved like a real geographical phenomenon. Did it remain over the ocean? Did it occupy the region described by the ship? Did it persist across more than one satellite pass? Did its shape and position correspond with the lemur's movement through the glowing water? Within the old data, a faint patch appeared. It was broad, soft-edged, far from the nearest coastline. The light was not concentrated into sharp points like ships or towns. It formed a dim, luminous region over the northwestern Indian Ocean, close to the position reported by the lemur. At first, such a signal might have seemed almost too weak to matter, but its location was difficult to ignore. The patch appeared in the same general part of the sea where the merchant vessel had entered the milky white water. Its timing also aligned with the date recorded in the ship's report. The more closely the two records were compared, the stronger the connection became. The lemur had seen the whitish glow ahead before entering it. Its officers had documented the ship's course. They had recorded how long the vessel remained within the luminous region. From those details, scientists could estimate the path the ship had taken through the event. When that route was placed over the satellite feature, the pieces began to fit. The ship's track passed through the luminous patch. The time of the encounter agreed with the satellite observation. The duration of the vessel's passage was consistent with the size of the glowing region. The pale mark was not merely near the lemur. It occupied the water through which the ship had traveled. The satellite data suggested that the Milky Sea covered approximately 15,400 square kilometers. It was an area larger than many major cities combined. From the deck of the lemur, the crew had seen only what the horizon allowed. They knew the white water extended in every direction, but they could not measure its full boundaries. The ship had been inside the phenomenon. Its scale was hidden by proximity. From space, the entire patch could be seen as one feature. The satellite offered distance. The vessel offered detail. Together, They revealed what neither could show alone. The satellite record also suggested that the luminous region persisted across multiple nights. This mattered greatly. A brief flash might have been caused by waves, lightning, or a temporary disturbance, but a broad patch remaining visible over several nights was consistent with sailors' descriptions of Milky Seas as stable and continuous events. It was not simply a momentary sparkle passing beneath one ship. It was a living region of ocean maintaining its glow over time. The old reports had often claimed that such seas could last for hours or days. Now there was evidence from orbit that a large luminous feature had endured beyond a single observation from the deck. For the first time, a Milky Sea described by sailors had been matched with a record made independently from space. The significance lay not only in the satellite image, it lay in the agreement between two very different forms of observation. One came from human beings standing aboard a ship. They saw the color of the water. They watched the glow surrounding the hull. They compared it to snow. They recorded the time and position. The other came from an instrument moving hundreds of kilometers above Earth. It could not feel the sea. It could not see shadows on the water. It could not describe the experience. It registered only a faint signal. Yet the two accounts pointed to the same place, the same night, the same immense patch of light. One can imagine the SS Lima crossing the White Sea below. Inside the bridge, officers watched the milky surface pass beneath the bow. Engines pulsed through the hull. Charts lay beneath quiet lamps. The crew had no way of seeing the full shape of the luminous region around them. Far above, a satellite moved silently through orbit. Its sensor looked down upon the dark curve of the ocean. Among the surrounding blackness, it recorded a pale mark. The people aboard the ship did not know the satellite had detected anything. The instrument in space knew nothing of the human observers below. The two records remained separate. One entered a ship's report. The other entered an archive. Years passed before anyone placed them side by side. Only then did the two perspectives meet. The sailors supplied what the satellite could not: the appearance of the sea from within it. The satellite supplied what the sailors could not: the scale and shape of the luminous field from above. Together, they transformed the event. The Lima report was no longer only an extraordinary eyewitness account. The satellite patch was no longer only an unexplained weakness in old data. Each gave meaning to the other. A mystery once preserved in handwritten logs had entered the age of orbital observation. The same light was seen from two directions, by sailors looking downward from a ship and by an instrument looking downward from space. How a satellite sees the night. The satellite that recorded the luminous patch near the SS Lima did not see the ocean as human eyes see it. It did not look down and recognize a white sea. It did not watch waves passing beneath a hull. It did not feel the darkness of a moonless night or compare the water to snow. Instead, it measured light, very small amounts of light. Some satellite instruments are designed to detect signals far weaker than daylight. During the day, sunlight dominates almost everything visible from orbit. Oceans reflect it, clouds scatter it, land surfaces return different colors and levels of brightness. At night, the world becomes quieter, but it does not become completely dark. Cities shine along coastlines and across continents. Fishing vessels form clusters of small lights over productive waters. Gas flares burn above offshore platforms and oil fields. Lightning flashes inside storms. Auroras spread across high latitudes. Moonlight reflects from clouds, deserts, ice, and the ocean surface. Even the upper atmosphere produces a faint natural glow known as air glow. A low-light satellite sensor must record all of these sources. Then scientists must determine which source produced each signal. This is why detecting a Milky Sea from space is difficult. A pale region over the ocean is not automatically biological. It might be a cloud reflecting moonlight. It might be a concentration of vessels. It might be sensor noise. It might be light scattered through the atmosphere from a distant coast. It might be a temporary feature caused by the angle of observation. The instrument records brightness. It does not provide an explanation. That work belongs to the scientist. A true Milky Sea candidate must therefore survive a series of questions. First, does the feature appear over open water? This seems simple, but coastlines are complicated at night. Bright cities can illuminate nearby clouds. Harbors contain ships, docks, platforms, and industrial lights. A glowing region close to shore may be difficult to separate from human activity. A candidate far from land is easier to study. The luminous patch associated with the lemur lay over the open ocean, well away from cities and coastlines. This reduced the number of possible explanations. Second, does the feature remain invisible during daytime reflectance checks? A cloud that appears bright at night may also appear clearly in daytime imagery. A bank of fog may reflect sunlight. A large patch of suspended dust or atmospheric haze may alter daytime observations. But a Milky Sea is not expected to form a bright, visible surface under sunlight. Its biological light is extremely weak compared with the day. If the nighttime patch has no corresponding daytime feature, the possibility of ordinary cloud or atmospheric material becomes less likely. Third, does the signal persist across multiple nights? Many sources are brief. Lightning lasts only moments. A ship moves. A fishing fleet may change position. Sensor noise may appear in only one image. Thin clouds may form and disappear. A large luminous region remaining visible over several nights behaves differently. Persistence suggests a real physical feature. It indicates that something stable enough to survive from one night to the next is producing the signal. The lemur-associated patch appeared across more than one night. That continuity supported the idea that the light came from a broad biological event rather than a momentary disturbance. Fourth, does the feature drift in a way consistent with ocean currents? A Milky Sea is part of the ocean. It should move with the water containing it. Its boundaries may stretch, bend, or shift as currents carry luminous particles and microorganisms. A land-based source will remain fixed. An offshore platform will remain in place. A fleet of vessels may move independently. A cloud will follow atmospheric winds rather than ocean circulation. If a faint luminous patch changes position slowly in a way that matches surface currents, the ocean itself becomes a more likely source. This does not prove the presence of luminous bacteria, but it strengthens the case. Fifth, can the feature be separated from ship lights, platforms, clouds, and coastlines? This requires careful comparison. Known shipping routes can be checked. The positions of offshore structures can be mapped. Weather data can reveal cloud cover. Moon phase and angle can be calculated. Daytime images can show whether visible clouds or surface features existed in the same region. A single image may remain ambiguous. Several independent checks can gradually remove the alternatives. The satellite patch connected with the lemur became convincing because it did not stand alone. It matched a detailed ship report. The crew had described a clear, moonless night. They had seen the glow directly on the water. They had recorded their course and position. The time of their passage agreed with the archived signal. The scale of the satellite feature agreed with the duration of the ship's journey through the White Sea. Human testimony gave the satellite mark context. Without the ship report, the faint patch might have remained an unexplained irregularity. Without the satellite data, the lemur account might have remained one more remarkable story from the deck of a vessel. Together, the two forms of evidence became much stronger. The satellite showed that the luminous region existed on a vast scale. The crew showed that the light came from the sea itself. Yet even with modern instruments, many obstacles remain. Moonlight can hide the signal. A bright moon illuminates the surface of the ocean and the clouds above it. This reflected light can be much stronger than the faint glow of a Milky Sea. The biological signal may disappear beneath the moonlit background. For this reason, moonless nights are especially important for detection. Clouds are another problem. A satellite looks down from above. If clouds cover the ocean, the sensor may see only their upper surfaces. A Milky Sea could glow beneath them without being recorded. Thin clouds may allow some light through, but distort its shape. Thick clouds can hide the phenomenon completely. This means that many Milky Seas may occur without ever becoming visible from orbit. The timing must be fortunate. The event must happen during darkness. The moon must not overwhelm it. Clouds must not conceal it, and the satellite must pass overhead while the glow still exists. Most marine bioluminescence is too faint or too brief to meet these conditions. The familiar sparks created by disturbed plankton occur on small scales. A wave flashes, a fish passes, a boat wake glows for a moment. These events may be brilliant to a nearby observer, yet almost meaningless from hundreds of kilometers above Earth. They are too small. They fade too quickly. Their light occupies too little of the satellite sensor's field. Milky Seas are different. They are detectable, not because each organism is unusually bright, but because the phenomenon is extraordinarily large and persistent. A very weak glow spread over thousands of square kilometers can become measurable. The individual light sources remain microscopic, but the combined surface creates a broad, stable signal. From orbit, scale can compensate for weakness. This is one of the strangest features of the phenomenon. A sailor may stand above intensely visible glowing water, while a satellite records only a faint patch. The human eye experiences the contrast between white sea and black night. The satellite reduces that experience to numbers. The sailor sees beauty and strangeness. The sensor sees radiance. Each observation is incomplete. The sailor cannot determine the full boundary of the event. The horizon limits everything. Even from the bridge of a large vessel, the crew sees only a small portion of the glowing field. They do not know whether it extends 10 kilometers or 100. They cannot easily distinguish its overall shape. They cannot observe how it changes from one night to the next after they leave. The satellite can see much farther. It can reveal the broad patch. It can compare one night with another. It can follow movement across the ocean, but it cannot stand inside the event. It cannot know that the sea looks like snow. It cannot see shadows falling from sailors onto the water. It cannot tell whether the glow is continuous beneath the clouds unless another source confirms it. It cannot identify the emotional force of the encounter. Technology extends vision. It does not replace experience. The Lima Report and the Satellite Archive demonstrate how different kinds of observation can strengthen one another. The officers aboard the ship recorded what they saw. The satellite recorded what its sensor measured. Years later, scientists brought these records together. The ship supplied location, appearance, duration, and physical context. The satellite supplied scale, persistence, and the view from above. The result was more than confirmation. It was a new method for studying an old mystery. Milky Seas no longer had to be found only by chance from the deck of a ship. In principle, they could be searched for from orbit. Historical archives could be examined. Future sensors could be designed to detect weaker signals. Ocean currents could be compared with luminous patches. Ships might one day be directed toward an event while it was still active. The White Sea had entered the satellite age. Still, the same caution remained. A satellite can record light without knowing its source. A sailor can witness a phenomenon without measuring its full extent. Knowledge appears when observations meet. A satellite can see farther than a sailor, but it cannot always understand what it sees. A sailor understands the experience, but cannot see its full extent. Together, the two observations become knowledge. When the old sailors were finally believed, long before satellites searched the night ocean, sailors had already described the White Sea. They had seen it from wooden decks, from merchant ships, from naval vessels, from steamships and sailing ships, crossing waters far from land. Their words differed slightly, but the images often returned. A snowfield, milky water, a phosphorescent sea, a white horizon, a continuous glow extending beyond the vessel in every direction. The names of the ships changed. The centuries changed. Navigation improved. Hull materials changed from wood to iron and steel. But the descriptions remained strangely familiar. The shooting star had crossed luminous water and carried the account forward in a ship's record. The CSS Alabama had moved through a pale sea beneath the stars, its sailors watching their own shadows fall across the glowing surface. Other merchant and naval ships reported similar encounters in the Arabian Sea and the Indian Ocean. Some captains wrote of a whiteness resembling snow. Some described the sea as covered in a milky haze. Others used the language available to them and called it phosphorescence. Though the light behaved differently from the brief sparks ordinarily associated with disturbed plankton, the details were not always complete. Some reports contained only an approximate position. Some lacked precise times. Some were written after the event rather than during it. Others survived only as references copied from one record into another. For much of modern scientific history, these accounts occupied an uncertain place. They were not easily dismissed. Too many sailors had described similar phenomena, yet they were also difficult to verify. The White Sea disappeared before scientists could reach it. The witnesses were often far from laboratories. The events occurred at night, over remote waters. No photograph remained. No instrument had measured the glow. A ship's log could preserve an observation, but not prove what produced it. This uncertainty encouraged doubt. Perhaps the sailors had mistaken moonlight for biological light. Perhaps low clouds had reflected distant sources. Perhaps imagination had strengthened the memory. Perhaps ordinary bioluminescence had been exaggerated by darkness and fatigue. A dramatic account written at sea could easily be treated as part observation, part folklore. Then the evidence began to change. In 1985, researchers aboard a vessel east of Socotra entered a Milky Sea and collected water directly from it. For the first time, the phenomenon entered bottles, microscopes, and laboratory notes. Luminous bacteria associated with organic material were found in the samples. The White Sea was no longer only something described from the deck. It had a biological connection. Still, the 1985 encounter could not reveal the full scale of the event. One vessel saw only the water surrounding it. One set of samples could not prove that every historical report had the same cause. The mystery remained open. Then came the SS Lima on January 25th, 1995. Its crew recorded a milky white sea approximately 150 nautical miles east of Somalia. They described a whitish glow ahead. They continued on course. 15 minutes later, the vessel entered a luminous region stretching from horizon to horizon. The sea resembled a field of snow. The glow remained continuous for hours. The ship's position, speed, heading, and time were recorded with modern navigational precision. Years later, those details were compared with archived satellite imagery. A faint, luminous patch appeared near the Lima's reported route. It matched the date. It matched the location. It aligned with the vessel's course, and with the length of time the ship remained within the glowing water. The patch covered approximately 15,400 square kilometers and persisted across multiple nights. This changed the meaning of the old reports. A white sea, described by sailors, had now been observed independently from orbit. The account from the deck and the signal from space supported one another. The phenomenon was physically plausible. It could cover an enormous area. It could remain visible for more than one night. It could appear as a continuous pale surface under moonless darkness. The language of the old sailors no longer seemed merely poetic. When the captain wrote that the sea resembled snow, the comparison could be understood as an accurate description of contrast. When a lookout described a white horizon, the phrase could reflect the real loss of distinction between glowing water and dark sky. When sailors reported a steady phosphorescent sea, they may have been observing not flashes, but a broad biological light that remained present before the ship disturbed it. The words had survived because they carried physical information: texture, color, distance, duration, continuity. The sailors did not possess modern vocabulary. They did not know about luminous bacteria. They did not know about quorum sensing. They could not describe organic particles, satellite radiance, or microbial ecology. But accurate observation does not always require a complete explanation. A sailor could record that the glow did not sparkle, that it stretched beyond the horizon, that the ship's wake looked dark against the surrounding whiteness, that the phenomenon lasted through several watches. These details mattered. They separated Milky Seas from ordinary flashes of marine bioluminescence. They gave later scientists something to compare. Historical ship logs began to take on a new scientific value. A logbook was not written as a modern dataset. Its pages might contain wind direction, sea state, weather, course, sail changes, engine conditions, discipline, illness, and routine events aboard the vessel. Yet among these entries were occasional descriptions of unusual light. When collected across many ships and many decades, those observations could reveal patterns. Researchers began assembling reports from several centuries. They compared dates, positions, seasons, moon phases, ocean regions, descriptions of color and durations. No single report could answer the mystery. Together, they formed a scattered archive of the ocean's rare behavior. The reports suggested that Milky Seas were not distributed randomly. Many occurred in the northwestern Indian Ocean. The Arabian Sea appeared repeatedly. Certain seasons seemed more common than others. Some regions east of Somalia and near Socotra returned again and again. These patterns could be compared with monsoon winds, currents, upwelling, phytoplankton blooms, and modern satellite observations. History became part of the scientific method. A captain's handwritten coordinates could help identify where a future event might occur. A note about a moonless night could help distinguish biological light from reflection. A description of several hours within white water could provide a minimum estimate of the event's size. A series of reports from similar seasons could suggest when ocean conditions became favorable. The old pages did not function like sensors, but they extended the human record far beyond the beginning of satellite observation. In this sense, the past became part of the instrument. Modern science often depends upon machines designed to make precise measurements. Satellites detect radiance, floats measure temperature and salinity, microscopes reveal cells, genetic tools identify organisms. But for Milky Seas, the observational system also included sailors who had crossed remote waters generations earlier. Their eyes had been the detectors, their language had been the storage medium, their logbooks had been the archive. The measurements were imperfect, positions could be uncertain, descriptions could vary. Some reports might contain error, yet imperfection did not make them useless. Science could compare them, test them, and search for consistency. The repeated language was significant. Snowfield, Milky Sea, white horizon, steady glow. These were not isolated inventions by one imaginative crew. They appeared across different vessels, nations, routes, and eras. The same oceanic behavior seemed to produce the same human comparisons. The satellite confirmation did not prove that every old account was accurate. Some reports may still have described other phenomena: moonlit fog, dense plankton flashes, reflected cloud, or distant lights could occasionally have been mistaken for a Milky Sea. But the Lima event established that the central claim was real. An ocean could glow continuously across thousands of square kilometers. A ship could travel for hours through pale water. The horizon could become white. The sailors had not been describing something impossible. They had been describing something rare. This distinction mattered. Folklore and science are not always enemies. Sometimes folklore contains repeated observation, waiting for the right method of verification. A legend may grow around an event, but the event itself can remain real beneath the stories. The task of science is not to believe every account without question, nor is it to reject every account that lacks modern instruments. It is to examine the evidence carefully, to compare sources, to test what can be tested, to discover whether patterns survive doubt. In the case of Milky Seas, the old sailors had preserved a pattern. Their descriptions traveled farther through time than the light itself. The glow faded after each encounter. The water returned to darkness. The ships continued toward distant ports, but the words remained. Generations later, scientists returned to those words with new tools. They read the logs again. They entered coordinates into maps. They searched satellite archives. They compared historical seasons with modern ocean conditions. And within those records, they discovered that the sea had been telling the same story all along. A pale surface beneath a moonless sky, a continuous light without sparks, a vessel crossing what appeared to be snow, a white horizon where the ocean should have been black. By 2005, the Milky Sea was no longer only a maritime legend. A research sample had linked the glow to luminous bacteria. A merchant ship's report had been matched with a vast patch of light observed from orbit. Historical accounts had become part of a developing scientific record. Yet one faint event, hidden in an old satellite archive, was only the beginning. The instruments that found it had not been designed for this purpose. The signal had been difficult to separate from noise. Clouds and moonlight could still conceal future events. Scientists needed a better eye in the night sky, and they needed another vessel willing to cross the glowing water.